You've probably heard both terms thrown around in sci-fi movies, maybe even used interchangeably. But here's the thing. One of them actually exists. The other? We're not so sure. And the difference between them is far stranger than fiction ever imagined. Let's start with what you can see. Or rather, what you can't see. A black hole is invisible. Not because it's hiding, but because it's doing something so extreme to reality that light itself can't escape. Imagine gravity so powerful that it bends space like a trampoline with a bowling ball on it, except the bowling ball weighs as much as a star, and the trampoline is the fabric of the universe itself. Everything near a black hole gets pulled toward a point called the singularity, a place where all the rules we understand completely break down. Wormholes are different. They're not objects at all. They're shortcuts. Think of the universe as a massive sheet of paper. If you want to get from one corner to the opposite corner, you'd normally have to travel across the entire surface. But what if you could fold that paper and punch a hole through both layers? You'd create a tunnel, a bridge between two distant points. That's a wormhole, a hypothetical tunnel through spacetime itself. Notice I said hypothetical. Black holes. We've seen them. We've photographed them. We've detected the gravitational waves they create when they collide. They're as real as the sun. Wormholes. Pure theory. Elegant mathematics. But zero evidence they exist anywhere in our universe. Here's where it gets interesting. Both concepts emerge from the same equations. Einstein's general relativity, published in 1915, describes gravity not as a force, but as the curvature of spacetime. Massive objects bend the fabric of reality around them. Einstein's equations are like a cosmic recipe book, and when physicists started solving them, they found multiple solutions. Some solutions described black holes, others described wormholes. The math works for both. But mathematics allowing something and nature actually creating it are two very different things. Black holes form through a process we understand reasonably well. When a massive star, at least 20 times the mass of our sun, runs out of fuel, it can no longer support itself against its own gravity. The core collapses catastrophically. In less than a second, all that mass compresses into a point smaller than an atom. The resulting gravitational field is so intense that it warps space-time into a one-way trap. Cross the event horizon, the boundary of no return, and you're done. You're not coming back, ever. We've observed this process indirectly thousands of times. We see stars orbiting invisible companions. We detect X-rays from matter heating up as it spirals into these gravitational monsters. We've even captured an image of the supermassive black hole at the center of the M87 galaxy, a shadow surrounded by a glowing ring of doomed material. Wormholes don't form through any known natural process. The equations say they could exist, but they also say something crucial. They're unstable. A wormhole, if it formed naturally, would collapse almost instantly. We're talking timescales shorter than the time it takes light to cross the width of an atomic nucleus. To keep a wormhole open, you'd need something called exotic matter. Not antimatter, not dark matter. Something that has never been observed and might not exist at all. This exotic matter would need to have negative mass and negative energy density. It would need to push space-time apart instead of pulling it together, essentially fighting against gravity itself. Does that sound impossible? It should, because we've never seen anything like it. Some physicists point to the Casimir effect, a quantum phenomenon where two metal plates placed extremely close together in a vacuum experience a tiny attractive force. The space between the plates has slightly less energy than the surrounding vacuum, creating what some interpret as negative energy. But this effect is minuscule, fleeting, and nothing close to what you'd need to stabilize a macroscopic wormhole. You'd need exotic matter in quantities that dwarf entire galaxies, and you'd need to arrange it in a precise configuration that probably violates several laws of physics we haven't fully explored yet. So why do scientists even talk about wormholes? Because the mathematics is too elegant to ignore. In 1935, Einstein himself, working with physicist Einstein-Rosen, discovered a solution to his field equations that described what we now call an Einstein-Rosen bridge. It connected two separate regions of space-time through a tunnel. The problem? Their bridge connected two black holes, and anything entering one would be crushed long before reaching the other side. Not exactly a usable shortcut. Decades later, physicists like Kip Thorne refined the concept. Thorne, working with his student Michael Morris in the late 1980s, figured out that if you had exotic matter, you could theoretically construct a traversable wormhole, one you could actually travel through without being destroyed. This work wasn't just academic daydreaming, it was rigorous physics, published in peer-reviewed journals, carefully exploring what the equations would permit under conditions that might, however unlikely, exist somewhere. But here's what nobody tells you in the movies. Even if wormholes exist, they come with problems that make black holes look simple. Time behaves strangely near both objects, but in different ways. Near a black hole, time slows down relative to someone far away. If you could hover just outside the event horizon, watching the universe, you'd see time speed up around you. Stars would age and die in what seemed like moments, but you'd still experience time normally from your own perspective. A wormhole creates a different kind of temporal weirdness. If the two mouths of the wormhole are in different gravitational fields, or if one mouth has been accelerated to high speeds and then brought back, the two ends could connect different moments in time. You might enter in 2024 and exit in 2034 or earlier. This is where causality starts screaming in protest. Imagine you travel through a wormhole to the past and prevent your younger self from entering it. Do you cease to exist? Does the universe split into parallel timelines? Do the laws of physics simply forbid this scenario from ever occurring? We don't know. The equations get murky when you introduce closed time-like curves, paths through space-time that loop back on themselves. Some physicists argue that quantum effects would destroy any wormhole before it could be used for time travel. Others suggest that the universe has some kind of chronology protection mechanism, a yet undiscovered law that prevents paradoxes. Stephen Hawking proposed this idea, half seriously calling it the chronology protection conjecture, noting that It would make the universe safe for historians. Black holes don't have this problem because they're not shortcuts. They're endpoints. Once you cross the event horizon of a black hole, every direction you move takes you closer to the singularity. Forward in time? Closer. Try to move sideways. Still closer. Attempt to go backward. The singularity is now in your future, unavoidable. Space and time swap roles inside the event horizon. The singularity isn't a place in space you can avoid. It's a moment in your future you cannot escape. What happens at the singularity? We honestly don't know. Our physics breaks down completely. General relativity predicts infinite density and infinite curvature of spacetime, which is physics speak for our equations stop working here. Quantum mechanics should become important at such extreme scales, but we don't have a complete theory of quantum gravity yet. The singularity is where our understanding hits a wall. Wormholes might avoid singularities entirely, at least in some theoretical models. The throat of the wormhole, the tunnel connecting two regions, could be smooth. No infinite densities, no breakdown of physics, just curved spacetime forming a bridge. But maintaining that bridge requires conditions so exotic they might be impossible. There's another crucial difference that gets overlooked. Black holes affect everything around them through gravity alone. You don't need to understand quantum mechanics or exotic matter to predict how a black hole will pull on nearby stars or bend passing light. The physics is well understood, tested, confirmed. Wormholes would require technology or natural processes we can barely conceive. Creating one artificially would mean manipulating spacetime at scales that make our most powerful particle accelerators look like children's toys. You'd need to concentrate energies that rival the Big Bang into a stable, controlled configuration, and somehow prevent the whole thing from either collapsing or exploding the moment you try to use it. The energy requirements alone are staggering. Some calculations suggest you'd need to convert an object the mass of Jupiter entirely into energy, then somehow channel that into creating and stabilizing the wormhole throat. And that's just to open a tunnel wide enough for a single proton to pass through. Want something human-sized? You're looking at energies that would require harvesting entire stars. This is why physicists talk about advanced civilizations on the Kardashev scale when discussing wormholes seriously. A Type 2 civilization, one capable of harnessing the entire energy output of their home star, might have the resources to attempt it. We're currently somewhere around Type 0.7, still dependent on planetary resources. But let's say, hypothetically, you had the technology, you've solved the exotic matter problem, you've got the energy, and you've somehow stabilized a wormhole. You'd still face navigation challenges that would make interstellar travel look easy. A wormhole doesn't come with a map. The throat could be curved, twisted, or branching. You might enter thinking you're heading to Alpha Centauri and exit somewhere in the Andromeda Galaxy, or in a completely different universe if the many worlds interpretation of quantum mechanics has any say in the matter. Black holes are predictable by comparison. If you know the mass, charge, and rotation of a black hole, you know everything there is to know about it. That's the no-hair theorem. Black holes have no complex features, no individuality beyond those three properties. They're simple objects, mathematically speaking. Wormholes would be anything but simple. Each one would potentially have a unique geometry, unique stability requirements, unique connections between distant or disparate regions of spacetime. Managing a network of wormholes would be like trying to maintain a subway system where the tracks randomly shift and the stations occasionally swap places. And we haven't even discussed what traveling through one would feel like. Near a black hole, tidal forces stretch objects. Your feet, closer to the singularity, would be pulled more strongly than your head. This spaghettification would eventually tear you apart. Though, for a supermassive black hole, you might survive crossing the event horizon intact. The tidal forces near the horizon of a billion solar mass black hole are surprisingly gentle. A wormhole's tidal forces would depend entirely on its geometry and the exotic matter distribution. Some theoretical wormholes would be smooth passages. Others might subject travelers to crushing gravitational gradients that would pulverize anything biological long before reaching the other side. You'd need to custom design each wormhole for safe passage, assuming that's even possible. There's also the radiation problem. Black holes emit Hawking radiation, a quantum effect where particle-antiparticle pairs form near the event horizon. One particle falls in, the other escapes, and from a distance it looks like the black hole is glowing with thermal radiation. For stellar mass black holes, this radiation is negligible, cooler than the cosmic microwave background. For tiny black holes, it would be intense. Wormholes might emit their own forms of radiation, especially if quantum effects near the throat become significant. Some calculations suggest that a wormhole would glow with exotic particles, possibly flooding both mouths with deadly radiation. You'd be building a shortcut through space that doubles as a particle accelerator pointed at both ends. Safety regulations for wormhole construction would be interesting to write. Despite all these challenges, the allure of wormholes persists in both science and imagination. The reason is simple. Black holes trap you, wormholes free you. One represents the ultimate prison, the other the ultimate escape route. One destroys information, the other preserves it while connecting distant realms. But this brings us to one of the deepest mysteries in modern physics, one that connects black holes and wormholes in ways that seem almost mystical. It's called the ER equals EPR conjecture, and it suggests that quantum entanglement, that spooky action at a distance Einstein never fully accepted, might actually be tiny wormholes connecting particles across space. If this conjecture is correct, then wormholes aren't just science fiction fantasies. They're woven into the quantum fabric of reality itself. Too small to use, but fundamental to how the universe operates at its deepest level. And black holes, those cosmic monsters we thought we understood, might be connected to distant regions of spacetime through microscopic bridges we're only beginning to comprehend. The line between black holes and wormholes isn't as clear as it first appeared. The mathematics that describes one bleeds into the mathematics of the other in ways that hint at deeper truths about the nature of space, time, and reality itself. Quantum mechanics tells us that when two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance and never liked it. He thought it violated the spirit of relativity, which says nothing can travel faster than light. But experiments have proven entanglement is real. Measure one particle's spin, and its entangled partner instantly takes the opposite spin, even if it's on the other side of the galaxy. Here's where things get weird. In 1935, Einstein and his colleagues Nathan-Rosen and Boris Podolsky published a paper challenging quantum mechanics. That same year, Einstein and Rosen published another paper describing bridges through spacetime, what we now call Einstein-Rosen bridges or wormholes. Two papers, same year, seemingly unrelated topics. Fast forward to 2013, and physicists Leonard Susskind and Juan Maldacena proposed something extraordinary. These two papers might describe the same phenomenon. The ER equals EPR conjecture suggests that every pair of entangled particles is connected by a tiny wormhole. ER stands for Einstein-Rosen, EPR for Einstein-Podolsky-Rosen. The idea is that quantum entanglement and wormholes are two ways of describing the same underlying reality. When particles become entangled, they're not communicating faster than light. They're connected through a microscopic tunnel in spacetime so small that nothing can actually pass through it. But the connection is real. This sounds insane until you look at the math. Black holes pose a problem called the information paradox. When matter falls into a black hole, it seems like the information about that matter is destroyed, which violates quantum mechanics. Information should be conserved. Stephen Hawking spent decades wrestling with this paradox. The ER equals EPR conjecture offers a potential solution. If entangled particles are connected by wormholes, then the information falling into a black hole might be preserved through these quantum connections, even if we can't retrieve it. Think about what this means. Your body contains roughly 10 to the 28 atoms. Many of those atoms contain electrons that were once entangled with other particles somewhere in the universe. If ER equals EPR is correct, you're connected to the cosmos through countless microscopic wormholes, a web of quantum threads linking you to distant stars, ancient supernovae, and particles scattered across spacetime. You're not separate from the universe. You're stitched into its fabric at the quantum level. But these aren't wormholes you could ever use. They're far smaller than atoms, probably around the Planck length, which is 10 to the negative 35 meters. That's to an atom what an atom is to a solar system. Nothing could travel through such a tiny passage. Even a single photon is too large. These quantum wormholes, if they exist, are features of spacetime's geometry, not shortcuts for travelers. They maintain connections between entangled particles without allowing anything to actually traverse them. The real question is whether macroscopic wormholes, the kind you could fly a spaceship through, have anything to do with these quantum connections. Some physicists think the answer is yes. Maybe large wormholes are just scaled-up versions of quantum entanglement, requiring exotic matter to keep them open, because you're essentially trying to make a quantum connection big enough for classical objects to pass through. Others think they're completely different phenomena that happen to share some mathematical similarities. What makes this especially mind-bending is what it implies about the nature of space itself. We think of space as the stage where physics happens, a backdrop against which particles and fields interact. But quantum mechanics suggests something different. Maybe space isn't fundamental. Maybe it emerges from quantum entanglement, from these microscopic connections between particles. Space might be what entanglement looks like when you zoom out. This idea, called emergent spacetime, is gaining traction among theoretical physicists. The geometry of space, the distances between objects, the very fabric of reality might all arise from the pattern of quantum entanglements between elementary particles. In this view, wormholes aren't shortcuts through space. They're the actual structure of space, normally too small to notice, but fundamental to how reality hangs together. Black holes fit into this picture in surprising ways. When you throw a book into a black hole, the information in that book doesn't vanish. It gets encoded on the black hole's event horizon in a scrambled form. This is called the holographic principle, the idea that all the information about what's inside a volume of space can be encoded on its boundary. A black hole's surface area tells you how much information it contains. Every bit of matter that falls in adds to that area. Now connect this to entanglement. The particles inside a black hole remain entangled with particles outside, connected through those quantum wormholes. The event horizon isn't just a one-way membrane. It's a massive tangle of quantum connections, linking the interior to the exterior. The black hole and the outside universe aren't separate systems. They're deeply entangled, bound together through microscopic wormholes that preserve information even as the classical geometry tells you nothing can escape. This suggests something profound about what happens when you fall into a black hole. From your perspective, you cross the event horizon and continue falling toward the singularity. But from the outside universe's perspective, you never quite reach the horizon. Your image gets frozen there, increasingly redshifted and dim, but never disappearing. Both perspectives are valid. The resolution might be that you and your quantum entanglement with the outside world take different paths through space-time, connected by wormholes too small to climb back through, but sufficient to preserve the information about your existence. The implications extend beyond black holes. If entanglement creates space-time geometry, then the Big Bang might have been the moment when the first quantum entanglements formed, when particles first became connected and space itself crystallized from a more fundamental quantum substrate. Before the Big Bang, there might not have been space or time in any recognizable sense, just a quantum state with no geometric structure. The universe's expansion could be the growth of entanglement, new connections forming between particles as they interact, weaving the fabric of space larger with each passing moment. This is speculative, but it's grounded in real physics. Physicists have shown that simple models of quantum entanglement can generate geometric spaces that behave like Einstein's curved spacetime. Start with a collection of quantum bits, entangle them in specific patterns, and out pops a geometry. Change the entanglement pattern, and the geometry changes. The equations match. The symmetries align. It works. What about those traversable wormholes we talked about earlier? If spacetime emerges from entanglement, then creating a wormhole might require engineering the quantum entanglement structure of space itself. You'd need to create a pattern of entanglements that generates a geometric shortcut. The exotic matter requirement might be a consequence of trying to maintain an unusual entanglement pattern that spacetime naturally wants to collapse. You're fighting against the tendency of quantum systems to minimize their energy and maximize their entropy. This brings us back to the practical question. Could any civilization actually build a wormhole? If ER equals EPR is correct, the answer might depend on whether you can manipulate quantum entanglement on macroscopic scales. We can entangle particles in labs. We've created entangled photons, atoms, even small molecules. But entangling enough particles in precisely the right pattern to generate a meter-wide wormhole, that's billions of orders of magnitude beyond current technology. You'd also face the problem of stability. Quantum entanglement is fragile. Interact with the environment, and the entanglement breaks. This is called decoherence, and it's why quantum computers are so difficult to build. Any interaction with outside particles destroys the delicate quantum state you're trying to maintain. A macroscopic wormhole would need to maintain its entanglement structure despite constant bombardment by cosmic rays, photons, gravitational waves, and every other field and particle in the universe. It would be like trying to keep a house of cards standing in a hurricane. Some physicists suggest that certain types of wormholes might be self-stabilizing if you get the geometry exactly right. The exotic matter distribution could create a configuration where quantum effects naturally maintain the entanglement structure. These would be solutions to Einstein's equations that are also solutions to quantum field theory equations, a sweet spot where general relativity and quantum mechanics agree. We haven't found such solutions yet, but we haven't proven they're impossible either. The connection between black holes and wormholes gets even stranger when you consider what's called a maximally extended black hole. Take the Schwarzschild solution, the simplest black hole geometry, and extend it mathematically as far as it can go. You get 4 regions. One is our universe outside the black hole. Another is the black hole interior. The third is a white hole, a time-reversed black hole that spits out matter instead of swallowing it. And the fourth is another universe entirely, connected to ours through the black hole's interior. This isn't science fiction. It's a legitimate solution to Einstein's equations. The catch is that this extended geometry describes an eternal black hole, one that has existed forever and will exist forever, never formed from a collapsing star. Real black holes form from matter collapse and don't have this extended structure. But the math suggests that if you could somehow create the right geometry, you'd get a bridge between universes. White holes are their own mystery. We've never observed one, and most physicists think they don't exist in nature. A white hole would be a region of spacetime where matter and light can only exit, never enter. The event horizon works in reverse. It's the past boundary of a region rather than the future boundary. Time flows backward compared to a black hole. If you approached a white hole, you'd see it exploding outward, ejecting matter with incredible energy. The problem is stability. Even if a white hole could form, quantum effects would likely destroy it almost instantly. Hawking radiation for a white hole would be intense and catastrophic. Some calculations suggest that white holes might exist for a fraction of a second during the formation of certain black holes, a transitional state that quickly collapses. Others think they're purely mathematical artifacts with no physical reality. But here's the twist. If wormholes exist, and if you can traverse one, you might encounter something like a white hole on the other side. Remember that wormholes connect two mouths through a throat. If one mouth is in our universe, and the other is in a different universe, or a distant part of our own universe, what would the second mouth look like from the other side? It might behave like a white hole, a region that spews out whatever enters from the first mouth. This creates a bizarre symmetry. Black holes trap, white holes expel. Wormholes connect them. You fall into the black hole mouth, travel through the throat, and emerge from the white hole mouth in another location. The journey would be one way because both mouths are event horizons, just oriented differently. You can enter the black hole side, but not exit it. You can exit the white hole side, but not enter it. The wormhole forces you to travel in one direction through space-time, unless you could somehow create a wormhole where both mouths are white holes or both are black holes. The physics of this is unclear. It might require exotic matter configurations so specific and unstable that nature forbids them. Or it might be possible in certain quantum states of geometry that we haven't discovered yet. The math is extraordinarily complex, and even supercomputers struggle to simulate these scenarios. What we do know is that the relationship between black holes and wormholes reveals something fundamental about the structure of space-time. They're not separate phenomena, but different aspects of how gravity can curve space and time. A black hole is what happens when matter collapses so completely that space-time folds in on itself, creating a one-way trap. A wormhole is what happens when space-time develops a bridge connecting distant regions. Both involve extreme curvature. Both require conditions we rarely encounter, and both challenge our understanding of reality. The fact that Einstein's equations allow both suggests that space-time is far more flexible than our everyday experience indicates. We live on a nearly flat surface, like ants on a vast sheet of paper. But that paper can be crumpled, torn, folded, and stitched together in ways we're only beginning to understand. Black holes are the crumples. Wormholes are the stitches. And somewhere in the mathematics of the extreme geometries lies the key to understanding what space and time really are. This isn't just abstract theory. Understanding the connection between black holes, wormholes, and quantum entanglement might be crucial for developing a theory of quantum gravity, the long-sought framework that unifies general relativity and quantum mechanics. Every attempt to merge these theories runs into problems. Infinities appear in the equations. Predictions become nonsensical. But by studying how quantum effects behave near black holes and within theoretical wormholes, physicists are finding clues about how to resolve these contradictions. One promising approach involves something called loop quantum gravity, which suggests that space isn't continuous but made of discrete loops at the smallest scales. In this framework, the singularity at a black hole's center might not be infinite. Instead, it could be a region where the loops of space are maximally compressed, creating enormous but finite density. This could turn black holes into wormholes, with the singularity replaced by a throat connecting to another region of space-time. Another theory, string theory, approaches the problem from a completely different angle. Here, the fundamental building blocks of reality aren't particles, but tiny vibrating strings. These strings can create all the particles we observe, and in this framework, black holes might be incredibly dense tangles of strings. When you fall toward a black hole's event horizon, you're not approaching a geometric point of infinite density. You're approaching a region where strings are wound so tightly that they create what looks like a singularity from the outside. But from the inside, from the perspective of the strings themselves, there's no infinity, just extraordinary compression. This string theory perspective suggests something radical. What if black holes don't have singularities at all? What if the apparent singularity is just our mathematical description breaking down because we're using the wrong tools? Imagine trying to describe the behavior of water molecules using only the rules of solid geometry. Your equations would predict impossible results because you're applying the wrong framework. Similarly, when we use classical general relativity to describe what happens at a black hole's center, we get infinities because we're not accounting for quantum effects that dominate at those scales. The resolution might lie in understanding that space-time itself has a quantum structure. Just as matter isn't continuous, but made of atoms, space and time might be composed of discrete units. At the Planck scale, roughly 10 to the negative 35 meters, space might stop being smooth and start resembling a foam of quantum fluctuations. At this scale, the concepts of here and there become fuzzy. The notion of a specific point in space loses meaning. And if space itself is grainy at the smallest scales, then the singularity, that infinitely small point of infinite density, simply cannot exist. Instead, what we call a black hole singularity might be a region where space-time reaches maximum quantum density. Beyond this density, the geometry of space itself prevents further compression. This creates what some physicists call a Planck star, a tiny but finite region at the black hole's core, where quantum effects halt the collapse. The matter doesn't disappear into nothingness. It compresses to the absolute limit that quantum geometry allows, then stops. This has profound implications for wormholes. If black holes don't contain true singularities, but rather Planck-scale structures, then their interiors might naturally form bridges to other regions of space-time. The quantum geometry could create a tunnel, a passage through the fabric of reality that connects distant points. You wouldn't need exotic matter to hold it open because the quantum structure of space itself provides the necessary support. The wormhole wouldn't be an artificial construction, but a natural consequence of how space-time behaves under extreme conditions. But there's a catch. Even if these quantum black holes naturally form wormholes, traversing them might be impossible for anything larger than subatomic particles. The throat of the wormhole could be so narrow, measured in Planck lengths, that not even a single atom could fit through. the wormhole would exist, connecting distant regions of spacetime, but it would be utterly useless for travel, like discovering a tunnel between two cities, only to find it's the width of a human hair. Yet, quantum mechanics offers a strange loophole. At quantum scales, particles don't have definite positions. They exist in superpositions, spread out over multiple locations simultaneously. An electron approaching the wormhole's throat wouldn't need to fit through in the classical sense. It could exist in a superposition of being on both sides of the wormhole, then collapse into a definite state on the far side. This quantum tunneling effect might allow information, if not matter, to traverse wormholes that are classically too small. This brings us back to quantum entanglement and the ER equals EPR conjecture. If entangled particles are connected by microscopic wormholes, then quantum tunneling through these wormholes could be what we observe as quantum correlation. When you measure one entangled particle, information doesn't travel through normal space to affect its partner. Instead, information travels through the quantum wormhole connecting them. The correlation appears instantaneous because the wormhole provides a shortcut through spacetime. This idea, if true, would revolutionize our understanding of both quantum mechanics and general relativity. It would mean that the spooky action at a distance that troubled Einstein isn't action at a distance at all. It's action through a hidden geometric connection, a wormhole so small we can't detect it directly, but large enough to allow quantum information to pass. The universe wouldn't be quite as non-local as quantum mechanics suggests. Instead, it would be stitched together by countless microscopic bridges invisible to our instruments, but fundamental to how reality operates. Testing these ideas presents enormous challenges. We can't directly observe what happens inside a black hole's event horizon. We can't create wormholes in laboratories. We can't peer into the quantum structure of spacetime with current technology. But we can test predictions that emerge from these theories. If quantum black holes exist, they should radiate in specific patterns. If microscopic wormholes connect entangled particles, certain quantum experiments should yield particular results. If spacetime has quantum structure, gravitational waves from colliding black holes should carry subtle signatures of that structure. Recent advances in gravitational wave astronomy have opened new windows into these questions. When LIGO detected gravitational waves from merging black holes, it confirmed that these cosmic behemoths exist and behave largely as general relativity predicts. But the data also contains information about what happens during the final moments of the merger, when the black hole's event horizons touch and combine. This is exactly the regime where quantum effects might become significant. Analyzing these gravitational wave signals with unprecedented precision might reveal deviations from classical predictions, hints that quantum geometry plays a role. Similarly, studying the radiation from black holes, the Hawking radiation that causes them to slowly evaporate, might provide clues. Hawking's original calculation suggested that black holes radiate purely thermal radiation, carrying no information about what fell in. This creates the black hole information paradox, because quantum mechanics insists that information can't be destroyed. If you throw a book into a black hole, the information about that book's contents should be preserved somehow. But thermal radiation carries no such information, implying that the information is lost forever. This paradox has haunted physics for decades. Recent work suggests that the resolution involves quantum entanglement between the radiation leaving the black hole and the matter remaining inside. As the black hole evaporates, information gradually leaks out through subtle correlations in the Hawking radiation. These correlations might be mediated by microscopic wormholes connecting the interior to the exterior, allowing information to escape without violating the event horizon's one-way nature. The mathematics describing this process is extraordinarily complex. It involves quantum field theory in curved spacetime, thermodynamics of horizons, and the holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary. Combining these frameworks reveals that black holes are far stranger than simple gravitational traps. They're information processors, quantum computers of cosmic scale, storing and manipulating data in ways we're only beginning to understand. And if black holes process information, what prevents us from using them as tools? Could we encode messages in matter, throw it into a black hole, and have that information emerge in another part of the universe through a wormhole? Could we use the quantum connections between entangled particles to create communication networks that exploit microscopic wormholes? These aren't idle speculations. Physicists are seriously investigating whether the structure of spacetime itself could be harnessed for information processing and communication. The challenges are formidable. Even if microscopic wormholes exist, controlling them would require manipulating quantum geometry with precision far beyond current capabilities. Even if black holes can transfer information through their interiors, extracting that information would require surviving conditions that vaporize matter. Even if entanglement creates geometric connections, using those connections for practical communication might violate the laws of quantum mechanics in subtle ways. But the theoretical possibility remains tantalizing. If spacetime is fundamentally quantum, if black holes and wormholes are different manifestations of the same geometric phenomena, if entanglement really does create bridges through space, then the universe is far more interconnected than we imagined. Distance might be an illusion created by our limited perspective. What appears as empty space might be threaded with invisible connections, quantum wormholes linking every particle to every other particle in a vast cosmic web. This web wouldn't be static. It would constantly evolve as particles become entangled and disentangle, as quantum states change and collapse, as the universe expands and matter rearranges itself. The geometry of spacetime wouldn't be a fixed stage where events occur. It would be a dynamic network of connections, constantly reconfiguring itself in response to quantum processes. Space and time would emerge from this network, like temperature emerges from the motion of molecules. Some physicists push this idea further, suggesting that space-time itself might not be fundamental. Just as temperature is a property of many moving particles, but doesn't exist for a single particle, space-time might be a collective property that emerges from quantum entanglement. The entanglement between particles creates the wormholes. The wormholes stitch together to form the fabric of space. and the evolution of this fabric gives rise to time. In this view, asking what space is made of is like asking what temperature is made of. It's the wrong question because space isn't made of anything. It's a pattern, a relationship, an emergent structure. This emergent space-time hypothesis connects to holography, the principle that information in a volume can be encoded on its boundary. A black hole's event horizon contains all the information about everything that fell in, encoded in a two-dimensional surface. Similarly, the universe's information might be encoded on its boundary, whatever and wherever that boundary is. We perceive 3 dimensions of space because that's how the information projects into the interior. But the fundamental reality might be 2-dimensional. Testing these ideas requires experiments at the intersection of quantum mechanics, gravity, and information theory. Some proposals involve creating analog black holes in laboratories using sound waves in fluids or light in special materials. These systems can't create actual gravitational black holes, but they can mimic the mathematical properties of event horizons. Studying how waves behave near these analogs might reveal universal principles that apply to real black holes. Other approaches focus on quantum entanglement experiments with increasing numbers of particles. If entanglement creates geometric connections, then highly entangled systems should exhibit spatial properties that correlate with their quantum correlations. Measuring these correlations with extreme precision might reveal signatures of underlying geometry, hints that space emerges from entanglement rather than existing independently. The implications extend beyond physics into philosophy. If space and time are emergent rather than fundamental, then our entire conceptual framework for understanding reality needs revision. We think of events happening in space and time, but if space-time emerges from quantum processes, then those processes must occur in some more fundamental arena. What is that arena? What does it mean for something to happen if not in space and time? These questions push against the limits of human comprehension, challenging our ability to think about reality without the scaffolding of spatial and temporal concepts. Perhaps the most radical answer is that happening itself is what creates space and time. Events don't occur in space-time. Space-time is the pattern of events occurring. When particles interact, when quantum states change, when information flows from one system to another, these processes create the geometric relationships we interpret as spatial distance and temporal duration. The universe isn't a container where things happen. It's the happening itself, constantly generating its own arena through the very processes we're trying to understand. This perspective transforms how we think about the fundamental laws of physics. Those laws might not describe how things behave in space and time. They might describe how space and time emerge from more primitive quantum information dynamics. Gravity wouldn't be a force pulling objects together across space. It would be a manifestation of how quantum information organizes itself, creating the illusion of spatial attraction between masses. The falling apple and the orbiting planet would be following the same information theoretic principles that generate space-time geometry. Some researchers explore these ideas through quantum computing and quantum information theory. A quantum computer manipulates information in fundamentally different ways than classical computers, exploiting superposition and entanglement to perform calculations that would take classical computers millions of years. These quantum information processes might be the bedrock reality from which spacetime emerges. The universe could be viewed as a vast quantum computer, processing information according to quantum rules, with space and time as outputs of that computation rather than inputs. This computational view connects to another mysterious aspect of quantum mechanics, the measurement problem. When you measure a quantum system, its wave function collapses from multiple possibilities into a single outcome. But what constitutes measurement? Does it require a conscious observer, or does any interaction count as measurement? The emergent spacetime perspective suggests a different interpretation. Measurement might be the process by which quantum information becomes encoded into geometric relationships. Before measurement, the quantum system exists in superposition, not localized in space. Measurement doesn't just reveal where the particle is, it creates the spatial relationship between the particle and the measuring device. Consider a photon traveling through space. In the standard view, it moves from point A to point B, existing at definite locations along the way, even if we don't observe it. But in the emergent view, the photon doesn't have a definite trajectory. It exists in quantum superposition, potentially taking all paths simultaneously. Only when it's absorbed by your eye or a detector does it become localized. And that localization is what creates the spatial relationship between the emission point and absorption point. The photon doesn't travel through space. Its absorption creates the space between source and detector. This sounds bizarre, but it resolves certain quantum paradoxes. The double-slit experiment, where particles behave like waves until observed, becomes less mysterious if observation is what creates definite spatial locations. The particle doesn't choose which slit to go through. The act of detection creates the geometric relationship that makes it appear to have gone through one slit or the other. Without detection, asking which slit it went through is meaningless because the spatial geometry required for that question doesn't exist yet. Quantum entanglement fits naturally into this framework. Two entangled particles don't occupy separate locations in pre-existing space. They're quantum correlated in a way that transcends spatial separation. When you measure one particle, you're not sending information across space to the other particle. You're collapsing the quantum state that encompasses both particles, and that collapse creates the spatial geometry that makes them appear separated. The correlation isn't traveling through space. The measurement is creating the space that gives meaning to their separation. This perspective suggests that quantum mechanics and general relativity might be describing different aspects of the same underlying reality. Quantum mechanics describes the fundamental information dynamics, how quantum states evolve and correlate. General relativity describes the emergent geometry that arises from those dynamics. They seem incompatible because we're trying to merge an emergent phenomenon with the processes that generate it, like trying to explain how molecules create temperature using a theory that assumes temperature exists fundamentally. The challenge is developing mathematical frameworks that capture these ideas precisely It's not enough to say space emerges from quantum information. We need equations that describe exactly how this emergence occurs, what quantum processes generate which geometric properties, and how the smooth, continuous spacetime of general relativity arises from discrete quantum events. Several approaches are being explored, each with different mathematical structures and philosophical assumptions. Loop quantum gravity takes the geometry of space itself and quantizes it, treating space as composed of discrete loops and nodes rather than continuous smoothness. In this framework, space has a granular structure at the Planck scale, roughly 10 to the minus 35 meters. Below this scale, the concept of distance breaks down. These quantum geometric building blocks connect and interact according to rules that generate the large-scale smooth geometry we observe. Time emerges from the evolution of these geometric structures, not as an independent parameter, but as a measure of change in the quantum geometric state. String theory approaches the problem differently, proposing that fundamental particles are actually tiny vibrating strings existing in higher dimensional space. The different vibrational modes of these strings correspond to different particles. Gravity itself emerges as one of these vibrational modes. In string theory, space-time isn't fundamental either. It emerges from the collective behavior of strings interacting according to string theory's equations. The extra dimensions predicted by string theory might not be physical spaces, but mathematical structures describing how quantum information organizes itself. Causal set theory offers another perspective, treating spacetime as a discrete set of events with causal relationships between them. Instead of smooth, continuous space, you have a network of events where some events can influence others and some cannot. The causal structure, which events can affect which other events, determines the geometry. Space and time emerge from counting how many events lie on causal paths between two events. This approach makes causality fundamental and geometry emergent. Each of these frameworks captures different aspects of what emergent spacetime might mean. They're not necessarily contradictory. They might be different mathematical descriptions of the same underlying reality, like how you can describe a circle using Cartesian coordinates or polar coordinates. The equations look different, but they describe the same geometric object. Similarly, loop quantum gravity, string theory, and causal set theory might be different coordinate systems for describing emergent spacetime. Testing these theories requires pushing into regimes where quantum effects and gravity both matter significantly. Black holes provide one natural laboratory. Near a black hole's event horizon, gravity is intense and spacetime curves dramatically. Inside the black hole, at the singularity, classical general relativity breaks down completely, predicting infinite densities and curvatures. This breakdown signals that quantum effects must become important. A quantum theory of gravity should resolve the singularity, replacing the infinite densities with some quantum geometric structure. The early universe provides another testing ground. At the moment of the Big Bang, the entire observable universe was compressed into a volume smaller than an atom. Quantum effects dominated, and spacetime itself was subject to quantum fluctuations. Understanding what happened at that moment requires a quantum theory of gravity. Different approaches make different predictions about the universe's initial state, predictions that might leave observable signatures in the cosmic microwave background or the distribution of galaxies. Gravitational waves offer yet another window. When massive objects like black holes collide, they create ripples in spacetime that propagate outward at the speed of light. We can now detect these waves directly using laser interferometers. As our detectors become more sensitive, we might detect subtle quantum features in these gravitational waves, deviations from classical predictions that reveal the quantum nature of spacetime geometry itself. Some physicists propose searching for signatures of emergent spacetime in precision measurements of quantum systems. If space emerges from entanglement, then systems with high degrees of entanglement should exhibit geometric properties correlated with their quantum correlations. Measuring these correlations with extreme precision might reveal how geometry emerges from quantum information. These experiments wouldn't directly observe Planck-scale physics, but they might reveal universal principles that govern the emergence of space from quantum processes. The philosophical implications ripple outward from physics into metaphysics and epistemology. If space and time are emergent rather than fundamental, what does this mean for our understanding of reality? We organize our entire experience around spatial and temporal concepts. Objects exist at locations in space. Events occur at moments in time. Causes precede effects temporally. If these concepts are emergent approximations valid only at large scales, then our everyday understanding of reality is a kind of useful fiction, accurate enough for practical purposes, but fundamentally incomplete. This connects to age-old philosophical questions about the nature of change and becoming. If time is emergent, does change happen fundamentally? Or is change itself an emergent phenomenon? Some interpretations suggest that at the deepest level, there is no change, no flow of time, just a timeless quantum state that encompasses all moments. The flow of time we experience emerges from how our consciousness processes information, from how memories form and causality operates in the emergent space-time. We perceive time flowing because our brains are macroscopic systems embedded in emergent time, not because time fundamentally flows. Others argue that change must be fundamental. Something must happen for space and time to emerge. That happening is change, suggesting that change is more primitive than time itself. Time emerges as a way of organizing and measuring these fundamental changes. This perspective treats process and becoming as bedrock reality, with static geometric spacetime as a derived concept, a useful but incomplete description of a fundamentally dynamic universe. These debates touch on questions about consciousness and observation. If measurement creates spatial relationships, if observation plays a role in collapsing quantum states into definite geometric configurations, then consciousness might be deeply connected to the emergence of space-time. Not that consciousness creates reality in some magical sense, but that the information processing we call consciousness is intimately linked to the information processing that generates emergent geometry. We're not outside observers studying space-time. We're processes occurring within the emergent structure. And our observations are part of what makes that structure definite. The idea that observation creates reality sounds mystical, but it might be addressing a genuine feature of quantum mechanics. Quantum systems don't have definite properties until measured. This isn't because we're ignorant of hidden variables. It's because definite properties don't exist until the quantum state collapses. If spatial location is such a property, then it doesn't exist definitely until the quantum state encoding position information becomes definite through interaction with other systems. Consciousness matters not because it's special, but because conscious observation is a particular kind of physical interaction that collapses quantum states. This raises questions about other emergent properties. If space and time emerge from quantum information, what else might be emergent? Mass, charge, spin. Are these fundamental properties or emergent features of quantum information patterns? Could the fundamental forces, electromagnetism, the strong and weak nuclear forces, even gravity, all be emergent phenomena arising from more primitive quantum processes? Some theories suggest yes, proposing that at sufficiently high energies, all forces unify into a single fundamental interaction, with the separate forces we observe at low energies being different manifestations of this unified force, broken symmetries that emerge as the universe cools. The search for such unification has occupied physicists for decades. Einstein spent his later years pursuing a unified field theory, trying to merge gravity and electromagnetism into a single geometric framework. He didn't succeed, partly because he didn't know about the nuclear forces, and partly because quantum mechanics wasn't fully incorporated into his approach. Modern attempts at unification take quantum mechanics as foundational, seeking to show how all forces and particles emerge from quantum fields or strings or loops of quantum geometry. These unified theories predict new particles and interactions that should become observable at extremely high energies, energies that existed only in the first moments after the Big Bang or in the most violent cosmic events. Particle accelerators try to recreate these conditions, smashing particles together at near light speed to probe what happens at high energies. Each new accelerator pushes further into this regime, discovering new particles and testing unification predictions. But there are limits. The energies required to directly observe Planck scale physics, where quantum gravity effects dominate, are astronomically beyond what any conceivable accelerator could achieve. The Planck energy is about 10 to the 19 times higher than what our most powerful accelerators can reach. Building an accelerator capable of reaching Planck energies would require a machine larger than the solar system. This seems physically and economically impossible, suggesting we need indirect methods to probe the quantum nature of space-time. Cosmology offers one such indirect route. The early universe was a natural particle accelerator, reaching energies far beyond anything achievable in laboratories. By studying the cosmic microwave background, the distribution of galaxies, and the behavior of matter in extreme environments like neutron stars and black holes, we can probe physics at scales inaccessible to direct experimentation. The patterns frozen into the cosmic microwave background preserve information about quantum fluctuations from the Planck era, stretched to cosmic scales by inflation. These fluctuations, initially microscopic quantum uncertainties, were amplified to become the seeds of all cosmic structure. Galaxies, stars, planets. Everything exists because of quantum fluctuations that occurred when the universe was smaller than an atom. If spacetime is emergent from quantum information, these primordial fluctuations might carry signatures of the underlying quantum structure. Subtle correlations in the temperature variations across the sky could reveal whether space is fundamentally discrete or continuous, whether it has preferred directions or is perfectly isotropic, whether information can truly be destroyed or is always conserved in some form. Current observations suggest space is remarkably smooth and isotropic at large scales, with no preferred directions or locations. This supports theories where space-time emerges from quantum states that don't themselves have spatial structure. The isotropy we observe isn't put in by hand, but emerges naturally from the underlying quantum dynamics. Yet small anomalies exist in the data. The cosmic microwave background has a cold spot, a region slightly cooler than expected. The distribution of temperature fluctuations shows subtle asymmetries between different hemispheres of the sky. These anomalies might be statistical flukes, or they could be hints of new physics. Perhaps they're signatures of the quantum structure underlying spacetime, tiny imperfections in the emergent geometry that betray its non-fundamental nature. Black holes provide another window into quantum spacetime. These objects are so dense that their gravitational fields become strong enough to significantly curve spacetime, creating regions where quantum effects and gravitational effects are comparable. The event horizon, that boundary beyond which nothing can escape, is a place where classical general relativity breaks down and quantum mechanics must be incorporated. Stephen Hawking discovered that black holes aren't entirely black. Quantum effects near the event horizon cause them to radiate particles, slowly evaporating over time. This Hawking radiation arises from quantum vacuum fluctuations near the horizon. Normally, virtual particle pairs appear and annihilate almost instantly. But near the event horizon, one particle can fall into the black hole while its partner escapes, becoming real radiation that carries energy away. This process creates a profound puzzle known as the black hole information paradox. When a black hole forms and eventually evaporates through Hawking radiation, what happens to all the information that fell into it? Classical general relativity says the information is destroyed, lost behind the event horizon, and eventually radiated away as thermal radiation that carries no information about what fell in. But quantum mechanics insists information cannot be destroyed. Every quantum process must be reversible in principle. If you know the final state precisely, you should be able to reconstruct the initial state. This contradiction suggests something fundamental is wrong with our understanding of black holes, spacetime, or quantum mechanics. Most physicists believe the resolution involves quantum properties of spacetime that classical general relativity doesn't capture. Perhaps information isn't actually destroyed, but is encoded in subtle correlations in the Hawking radiation. Correlations that would require understanding quantum gravity to detect. Or perhaps the event horizon isn't as simple as classical relativity suggests. Having a quantum structure that preserves information even as matter crosses it. String theory offers one potential resolution through the holographic principle. This radical idea suggests that all the information contained in a volume of space can be encoded on its boundary, like a hologram encoding three-dimensional information on a two-dimensional surface. For black holes, this means all the information that falls in is actually encoded on the event horizon, never truly entering the interior. The interior might even be an emergent description that arises from quantum dynamics on the horizon. If this is correct, it implies something extraordinary about space itself. Three-dimensional space might be emergent from information encoded on two-dimensional boundaries. The volume we experience might be a holographic projection, with the fundamental reality being lower dimensional. This doesn't mean we live in a simulation. It means the dimensionality of space is itself emergent, not fundamental. Evidence for holography comes from calculations showing that the maximum entropy, the maximum information content that can be stored in a region of space, is proportional to the area of its boundary, not its volume. This is surprising. You'd expect that doubling the radius of a sphere would increase its information capacity by a factor of 8, since volume scales as radius cubed. But black hole thermodynamics and quantum gravity calculations suggest it only increases by a factor of 4, since area scales as radius squared. This area law for entropy suggests space has one less dimension than it appears to have. The extra dimension is somehow redundant, emergent from information encoded on lower dimensional boundaries. Researchers have made this concrete in special cases, showing that certain quantum field theories in one dimensionality are exactly equivalent to gravitational theories in one higher dimension. The gravitational theory emerges from the quantum theory, like spacetime emerging from quantum information. These holographic dualities are more than mathematical curiosities. They're computational tools for studying quantum gravity. Questions that are impossibly hard in the gravitational theory become tractable in the dual quantum theory, and vice versa. By translating between descriptions, physicists can probe aspects of quantum spacetime that would otherwise be inaccessible. But holography raises new questions. If space is emergent and holographic, what determines which boundary encodes which bulk region? Can multiple boundaries encode the same volume? What happens at the boundaries of the universe, if there are any? Does the entire cosmos have a holographic jewel? And if so, where is that jewel theory located? Some proposals suggest the ultimate boundary is the cosmological horizon, the limit of what we can observe. All the information in our observable universe might be encoded on this horizon, with the three-dimensional space we experience being an emergent holographic projection. As the universe expands, the horizon grows, and more information becomes encoded, allowing more complex structures to emerge. This perspective transforms how we think about cosmic evolution. It's not just matter rearranging itself in space, it's information processing on the cosmic horizon, generating increasingly complex emergent patterns. Patterns we interpret as galaxies, stars, planets, and life. We're not separate from this process. We're part of the information being processed, temporary patterns in the holographic projection of cosmic data. Quantum error correction provides another angle on emergent spacetime. Information theory shows that robust storage and transmission of information requires redundancy. Multiple physical systems must encode the same logical information so that if some systems are corrupted, the information can still be recovered. This is how computer memory works, how communication protocols handle noise, how DNA replicates despite occasional errors. Recent work suggests space-time itself might be a quantum error-correcting code. The redundancy required to protect quantum information from errors naturally generates geometric structure. Multiple qubits must be arranged in particular patterns to form a code. And these patterns can be interpreted as points in an emergent space. The connections between qubits, the correlations in their quantum states, define distances and angles in this emergent geometry. When quantum information is encoded properly with sufficient redundancy, the emergent geometry is smooth and continuous, resembling the spacetime of general relativity. But if the encoding is corrupted, if quantum errors accumulate, the geometry becomes ill-defined, potentially breaking down entirely. This offers a new perspective on singularities, those points where classical spacetime becomes infinite and general relativity fails. Perhaps singularities are locations where the quantum error-correcting code has failed, where too much information has been corrupted for the geometric description to remain valid. Black hole interiors might be such regions. The classical description shows curvature becoming infinite at the singularity, but the quantum description might reveal this as a breakdown in the error-correcting code that generates spacetime. Information isn't destroyed. It's scrambled beyond the point where geometric language applies. New mathematical frameworks beyond geometry might be needed to describe what happens there. This connects to the measurement problem in quantum mechanics. When you measure a quantum system, its wave function appears to collapse from a superposition of possibilities into a definite outcome. But quantum mechanics doesn't explain how or why this collapse occurs. It's often treated as a separate postulate, added to the theory by hand rather than derived from deeper principles. If spacetime is emergent from quantum information, measurement and collapse might be related to the emergence of definite geometry. Before measurement, quantum systems exist in superpositions that don't correspond to definite locations in space. Measurement causes the quantum state to become entangled with the environment, creating correlations that define a particular spatial configuration. The wave function collapse might be the emergence of definite spatial relationships from previously indefinite quantum information. This doesn't solve the measurement problem completely, but it reframes it. Instead of asking why quantum states collapse, we ask why quantum information becomes organized in ways that generate classical spacetime. The answer might involve decoherence, the process by which quantum systems become entangled with their environments, losing their quantum coherence and behaving classically. Decoherence occurs rapidly for macroscopic objects, explaining why we don't observe superpositions of everyday things. A single dust particle interacting with air molecules becomes entangled with billions of atoms almost instantly, destroying any quantum superposition. This entanglement generates classical correlations, the kind of information that creates definite spatial relationships. For microscopic systems isolated from their environment, decoherence is slower, allowing quantum superpositions to persist. These systems don't have definite locations because they haven't yet become sufficiently entangled with their surroundings to generate the classical information that defines position. Space, for such systems, is genuinely indefinite, not yet emerged. This suggests consciousness might be relevant, not because it's magical, but because conscious observation represents a particular kind of physical interaction that rapidly generates classical correlations. When you observe a quantum system, you become entangled with it through a measurement apparatus, and this entanglement creates the information that defines spatial relationships. You don't create space through some mystical power of mind. You participate in the physical process that makes spatial descriptions applicable. Time might emerge similarly. Quantum states evolve according to the Schrödinger equation, which describes how quantum information transforms. But this evolution is reversible and doesn't single out a direction. There's no fundamental arrow of time in quantum mechanics. Yet we experience time flowing in one direction, from past to future, with causes preceding effects and entropy increasing. The thermodynamic arrow of time, the tendency for entropy to increase, might be connected to the emergence of spacetime. As quantum systems become entangled and decohere, classical information is generated. This process is irreversible. Once quantum coherence is lost, it cannot be recovered without expending enormous effort. The accumulation of classical correlations, the growth of entanglement entropy, might be what we experience as the flow of time. In this view, time isn't fundamental. It's an emergent description of how quantum information becomes organized into patterns we recognize as classical histories. The past is the set of quantum correlations that have already been established. The future is the space of possible correlations that might emerge. The present is the ongoing process of quantum information becoming classical, of indefinite possibilities collapsing into definite actualities. This makes time's arrow a consequence of the same process that generates space. Both emerge from the organization of quantum information, with space being the structure of current correlations and time being the accumulation of those correlations. Spacetime isn't a pre-existing stage. It's a description of how quantum information is arranged and how that arrangement evolves. Causality itself becomes emergent. In fundamental quantum mechanics, there's no notion of cause and effect, only correlations between quantum states. But as decoherence generates classical information, certain correlations become interpretable as causal relationships. Event A causes event B because the quantum correlation between them has a structure that's naturally described in causal language, with information flowing from A to B rather than vice versa. This doesn't mean causality is illusory. It means causality is a high-level description that emerges when quantum information is organized in particular ways, just as temperature emerges from molecular motion and is perfectly real despite not being fundamental. Causality emerges from quantum correlations and is perfectly real despite not being written into the deepest laws. These ideas remain speculative, theoretical frameworks seeking experimental confirmation, but they're being tested indirectly through cosmological observations, black hole physics, and tabletop quantum experiments. Each new piece of data either supports or constrains these proposals, gradually sharpening our understanding of whether spacetime is truly emergent or fundamentally real. The stakes are high. If spacetime is emergent, our entire picture of reality shifts. We're not objects moving through space and time. We're patterns in quantum information that interpret themselves as existing in space and time. The universe isn't a container with contents. It's information processing itself, generating the appearance of containers and contents as useful descriptions of its own structure. Human existence takes on new meaning in this framework. We're not separate observers studying reality from outside. We're part of the information being processed, localized patterns of quantum correlations complex enough to model themselves and their environment. Consciousness itself becomes a puzzle viewed through this lens. If spacetime emerges from quantum information, what does that make awareness? The traditional picture treats consciousness as something happening inside brains, inside skulls, inside space. But if space isn't fundamental, this picture dissolves. Some researchers propose consciousness might be tied to quantum coherence in neural structures. The brain maintains delicate quantum states that process information in ways classical computation cannot. When these states decohere, they generate the classical correlations we experience as conscious moments. Awareness might be the subjective experience of quantum information becoming classical, the feeling of possibilities collapsing into actualities. Others suggest consciousness requires a particular type of information integration. The brain doesn't just process information, it creates unified models where different sensory streams merge into coherent experiences. This integration might depend on how quantum correlations are structured across neural networks. The more integrated the information, the richer the conscious experience. These ideas face enormous challenges. We don't understand consciousness well enough to connect it rigorously to quantum mechanics. Neural processes seem too warm and messy to maintain the delicate quantum coherence these theories require. The brain might use classical information processing exclusively, with quantum effects playing no special role. Yet the hard problem of consciousness, why subjective experience exists at all, remains unsolved by classical approaches. If physical processes are just matter moving through space according to equations, why does it feel like something to be a brain processing information? Why isn't there just darkness, unconscious computation without inner experience? Emergent space-time frameworks suggest a possible answer. If reality is fundamentally information, rather than matter moving through pre-existing space, then experience might be what information processing feels like from the inside. Consciousness isn't something extra added to physical processes. It's what certain types of information processing are. Intrinsically, this doesn't solve the hard problem, but it reframes it. Instead of asking why matter generates consciousness, we ask what types of information structures have intrinsic experiential character. The question shifts from bridging a gap between physical and mental to understanding which patterns of information are conscious and why. The implications extend to questions about other minds. If consciousness relates to information integration, then anything that processes information in sufficiently complex ways might have some form of experience, not necessarily human-like consciousness, but something, a perspective, however alien. This makes consciousness potentially ubiquitous, not in mystical ways, but as a gradient property that emerges wherever information is processed with sufficient integration. Simple systems have minimal, primitive experience. Complex systems, like brains, have rich, structured consciousness. The universe might be filled with varying degrees of awareness, most nothing like human consciousness, but real nonetheless. Free will takes on new dimensions in emergent spacetime. The traditional debate assumes a fixed future already exists, either determined by physical laws or open to genuine choice. But if time emerges from quantum information becoming classical, the future doesn't exist yet, not even as determined possibilities. It's genuinely undecided. Quantum mechanics preserves genuine randomness at fundamental levels. When quantum states decohere, which classical outcome emerges has irreducible probabilistic character. This isn't ignorance about hidden variables. Experiments confirm nature itself doesn't decide which outcome occurs until decoherence happens. If free will exists, it might work through quantum indeterminacy. Decisions aren't predetermined because the quantum information constituting your brain hasn't collapsed into classical correlations, representing those decisions yet. When you choose, quantum possibilities become classical actualities. The choice is yours because the information processing, generating that choice is you. This doesn't make decisions arbitrary. Your quantum state reflects your history, values, knowledge, everything making you who you are. When that state decoheres into a decision, the outcome reflects those accumulated influences. It's determined by your character without being predetermined before you choose. Critics argue this just replaces determinism with randomness, neither providing genuine agency. If quantum outcomes are probabilistic, decisions seem random rather than freely chosen. But this misses something crucial. The probabilities aren't external to you. They're determined by your quantum state, which encodes everything you are. The randomness is constrained by your nature. Moreover, consciousness might influence which quantum outcomes become classical. If awareness relates to how information integrates during decoherence, then conscious deliberation might affect probability distributions over outcomes, not by violating quantum mechanics, but by determining how quantum information is structured when it becomes classical. These remain highly speculative ideas, far from established science, but they illustrate how emergent space-time frameworks reshape fundamental questions about mind, choice, and existence. If reality is information generating the appearance of space and time, everything we thought we understood requires reconsideration. The nature of identity shifts dramatically. You're not a fixed object persisting through time. You're a pattern in quantum information that maintains coherence despite constant change. Every moment, quantum correlations constituting your brain and body decohere into new classical states. The pattern persists, but the information is always processing, always becoming. This makes personal identity both more robust and more fluid than traditional views suggest. More robust Because identity doesn't depend on particular atoms staying in place. Your atoms are constantly replaced, but the information pattern continues. More fluid because there's no unchanging essence, just evolving correlations maintaining recognizable structure. Death becomes transition rather than ending. When your brain stops maintaining the quantum coherences that generate your consciousness, those particular information patterns cease, but the quantum information itself doesn't vanish. It redistributes into other correlations, other patterns. You as a distinct pattern end, but the information that was organized into you returns to the universal process. This provides no comfort of afterlife or resurrection. The pattern that was you genuinely terminates, but it suggests reality is fundamentally creative, constantly processing information into new forms. The universe that generated your pattern will generate countless others, each unique, each temporary, each part of the ongoing emergence of classical reality from quantum possibility. Purpose and meaning transform in this framework. If we're information patterns rather than fixed objects, our significance comes from what we contribute to the universal process of information becoming organized. We're how the universe experiences certain perspectives, processes certain questions, generates certain insights. Human civilization becomes a collective information processing system of staggering complexity. Language, culture, technology. These are mechanisms for integrating information across individual minds, creating correlations that transcend individual brains. Society is itself an emergent pattern arising from quantum information organized through billions of interacting conscious systems. Science itself is the universe developing self-understanding through these collective patterns. When physicists discover quantum mechanics or mathematicians prove theorems, information organized in human form is processing information about its own nature. The universe is literally figuring itself out through us. This makes knowledge valuable beyond practical applications. Each genuine insight, each true understanding represents information achieving new forms of organization. When you learn something real about reality, you're participating in the cosmic process of information structuring itself. Understanding has intrinsic worth because it's the universe becoming conscious of its own nature. Art, beauty, love. These two become information patterns with objective significance. They're not mere subjective preferences, but genuine structures in how quantum information can organize itself. A beautiful symphony represents information arranged in ways that resonate with how consciousness integrates information. Love reflects quantum correlations between people, creating unified patterns that transcend individuals. The emergent spacetime framework suggests ethics has foundation beyond human convention. If consciousness relates to information integration, then causing suffering means disrupting coherent information patterns in ways that generate negative subjective character. Helping others thrive means supporting the emergence of richer, more integrated information structures. This doesn't provide simple moral rules, but it grounds ethics in something beyond arbitrary preference. Actions matter because they affect how information organizes itself, which determines what experiences emerge. We're not isolated individuals in indifferent space. We're interconnected patterns whose organization affects what the universe experiences through us. Cosmology gains human relevance through this lens. The history of the universe isn't just background to human concerns. It's the story of how quantum information has organized itself into increasingly complex patterns, from quantum foam after the Big Bang to the first particles, from stars forging heavy elements to planets supporting life, from simple organisms to conscious beings, asking why anything exists. This is information, exploring what structures it can form. We're not separate from that process, observing from outside. We're the current frontier. Information organized so complexly, it can model itself, question its own nature, deliberately create new patterns. Every thought you think, every choice you make, every connection you form with others is the universe continuing its exploration of what's possible. This framework faces formidable obstacles before earning acceptance. It must make testable predictions distinguishing it from alternatives. It must explain how specific quantum information structures generate classical spacetime with particular properties. It must connect rigorously to established physics rather than remaining philosophical speculation. Researchers pursue multiple approaches. Some focus on black hole thermodynamics, where information theory meets gravity most dramatically. Others study cosmological observations that might reveal quantum structure underlying spacetime. Still others design quantum experiments, testing whether spacetime shows discrete structure at tiny scales. The mathematics grows increasingly sophisticated. Tensor networks model how quantum entanglement might weave spacetime together. Category theory provides abstract frameworks for how information generates geometry. Quantum error correction codes suggest spacetime might protect quantum information from decoherence, explaining why classical reality is so stable. Each advance reveals new puzzles. How does continuous spacetime emerge from discrete quantum information? Why does space have 3 dimensions rather than 2 or 17? How do particles with mass and gravity fit into purely informational pictures? What determines which information structures become classical versus remaining quantum? These aren't failures. They're signs of genuine progress. Science advances by discovering better questions, not by claiming final answers. The fact that emergent spacetime frameworks generate precise, difficult questions means they're mature enough to test against reality. The philosophical implications continue deepening. If spacetime emerges from quantum information, what does that make mathematics? Is math discovered or invented? If reality is information processing itself, perhaps mathematics is the language information uses to structure itself. Mathematical truth might be statements about which information patterns are self-consistent. This makes mathematics both objective and emergent. Mathematical facts are real because certain information structures genuinely cannot exist. Contradictions aren't just forbidden by rules, they're impossible configurations of information. But mathematics emerges from information rather than existing in Platonic realm, separate from physical reality. Logic itself becomes emergent. The basic rules of reasoning, if A, then B, not both A and not A, either A or not A, might reflect how classical information must organize to be consistent. Quantum mechanics already violates some classical logic rules, suggest this logic emerges when quantum information decoheres into classical form. This doesn't make reasoning arbitrary. The information structures supporting conscious thought require classical logic to function. We can't think contradictions because our brains are classical information processors. Logic is how information must organize to support thought, making it necessary for consciousness despite being emergent. Language takes on new significance. Words aren't just labels for pre-existing things. They're tools for organizing information into patterns that can be shared between minds. When you understand these words, quantum correlations in your brain are structuring themselves to mirror information patterns the words represent. Communication is literally quantum information in one brain influencing how information organizes in another. This explains why language can be precise yet flexible, why meanings shift with context, why perfect communication is impossible, but partial understanding always achievable. Information patterns never transfer perfectly between systems, but they can create correlations that approximate shared structure. The relationship between observer and observed dissolves. In traditional pictures, you're separate from what you study, but if you're information patterns, and so is everything you observe, studying reality means information examining its own structure. There's no fundamental distinction between subject and object, just different levels of information organization. Quantum mechanics already hints at this through measurement. Observation doesn't passively record pre-existing facts. It creates correlations between observer and observed, generating the classical information we experience as measurement results. The act of knowing changes what's known, because knowing creates quantum correlations that didn't exist before. Human existence gains cosmic context without losing personal significance. You're not a tiny accident in an indifferent cosmos. You're how the universe processes information about itself at human scales. Your consciousness is reality examining its own structure through biological information processes. Every thought you have adds new quantum correlations to the cosmic web. Every decision you make reorganizes information patterns that ripple outward through spacetime. You matter because you're where information becomes aware of itself. But this cosmic significance doesn't erase personal meaning. Your specific thoughts, relationships, experiences remain uniquely yours. They're particular information patterns that exist nowhere else in the universe. Your perspective is an irreplaceable viewpoint from which reality knows itself. The universe contains countless such perspectives, each adding unique structure to the whole. Death takes on different character. When your brain stops processing information, the specific quantum correlations supporting your consciousness decohere into classical states. Your particular viewpoint ceases, but the information that structured your experience doesn't vanish. It disperses into the environment, becoming available for reorganization into new patterns. You're a temporary eddy in information flow, not a separate thing that can be destroyed. The information constituting you existed before your birth in different forms and will continue existing after your death in different configurations. What makes you you is the particular pattern, not the information itself. This doesn't trivialize death or eliminate grief. The specific information pattern that is you will will genuinely cease existing. That particular way of organizing information is finite and precious. But it suggests death isn't annihilation into nothingness. It's reorganization into different information structures. Consciousness might have quantum aspects that persist beyond brain death in ways we don't yet understand. If experience correlates with certain quantum information patterns, and quantum correlations can span space and time in non-local ways, perhaps some aspects of consciousness are less localized than we assume. This isn't wishful thinking disguised as physics. Quantum biology is discovering that brains might exploit quantum effects in ways previously thought impossible in warm, wet environments. Photosynthesis uses quantum coherence. Birds navigate using quantum entanglement in their retinas. Enzymes may use quantum tunneling. If evolution discovered how to harness quantum effects for biological function, consciousness might involve quantum information processing that doesn't neatly reduce to classical neural activity. This doesn't require mysticism, just recognition that quantum mechanics applies to biology as much as physics. The hard problem of consciousness, why subjective experience exists at all, might connect to quantum measurement. When quantum possibilities collapse into classical outcomes, information that was in superposition becomes definite. This transition from quantum to classical information might be what generates the qualitative feel of experience. Consciousness could be what quantum to classical transitions feel like from the inside. The measurement problem in quantum mechanics asks why observation produces definite outcomes from quantum superpositions. The hard problem of consciousness asks why information processing produces subjective experience. Perhaps these are the same question viewed from different angles. This doesn't solve either problem completely. We still don't know exactly how quantum decoherence produces classical reality, and we still don't know how neural information processing produces qualia. But linking them suggests consciousness isn't separate from physical processes. It's the subjective aspect of certain information transitions that occur throughout nature. If this is correct, consciousness might be more widespread than commonly assumed. Wherever quantum information decoheres into classical form, some primitive proto-experience might occur. Human consciousness would be an extremely sophisticated version of a basic feature of how information organizes itself. This doesn't mean rocks are conscious. Classical information patterns in rocks are too simple to support anything recognizable as experience. But it suggests the capacity for experience might be fundamental to how information structures reality, with human consciousness representing highly organized expression of this basic feature. The unity of consciousness, your sense of being a single experiencer, might reflect how information integrates across quantum systems. Your brain creates a unified field of quantum correlations that decohere together, producing integrated classical information experienced as singular perspective. When these correlations break down during sleep or anesthesia, the unity fragments. This explains why consciousness seems indivisible, despite brains having multiple parts. Information integration creates a single quantum state spanning neural networks, which collapses into unified classical experience. You feel like one thing because you're one information pattern, even though that pattern emerges from billions of neurons. Free will takes on new dimensions. If you're information processing itself, rather than something separate from physical processes, the question isn't whether you have free will, but what kind of freedom information patterns can have. Classical determinism seems to eliminate freedom. If the universe is clockwork following fixed laws, your choices are predetermined. But quantum mechanics introduces genuine randomness. Does that help? Not obviously. Random choices aren't free. They're just unpredictable. But if information is fundamental and you're a self-referential information pattern, freedom might mean something different. You're not separate from the physical processes determining your actions. You are those processes. When you make decisions, information is organizing itself according to its own structure. That's not freedom from causation, but it might be the only kind of freedom possible. Your decisions emerge from quantum information patterns that include your entire history, current context, and future goals all entangled together. You're not a passive observer of predetermined events. You're an active pattern shaping how information flows through you. The question isn't whether you could have chosen differently under identical conditions, but whether your information structure genuinely influences outcomes. It does. Your beliefs, knowledge, and values are information patterns that causally affect how you process new information and generate decisions. This influence is real even if the overall process is deterministic. You have the kind of freedom that matters. Your internal structure genuinely shapes your actions. Quantum randomness might provide additional freedom. If consciousness involves quantum processes, your decisions might incorporate irreducible quantum uncertainties. This doesn't make choices random. It means they're influenced by quantum fluctuations integrated into coherent decision processes. The randomness isn't you flipping coins. It's quantum information contributing to classical outcomes in ways that increase your decision space. You become less predictable without becoming arbitrary. This is compatible with feeling free, the sense that you're authoring your actions rather than passively experiencing predetermined events. Moral responsibility survives this framework. You're accountable for your actions because they genuinely flow from your information structure. Your character, knowledge, and choices are real causal factors. Holding people responsible means recognizing that their internal information patterns matter, that we can influence behavior by changing those patterns through consequences and incentives. This doesn't require libertarian free will, where you could have chosen differently under identical conditions. It requires that your information structure genuinely affects outcomes and can be modified by experience. Both are clearly true. Your decisions emerge from your specific information patterns, and those patterns change based on consequences. Justice becomes about managing information flow through social systems. Punishment modifies information patterns in ways that reduce harmful behavior. Rehabilitation reorganizes criminal information structures. Deterrence creates information that influences potential offenders. None of this requires metaphysical free will. just recognition that information patterns matter and can change. Creativity and discovery gain new meaning. When you have insights or create art, you're not accessing Platonic realm of pre-existing ideas. You're reorganizing information into novel patterns that didn't exist before. The universe is literally creating new information structures through your conscious activity. Mathematical discoveries aren't uncovering eternal truths existing outside reality. They're finding which information structures are self-consistent. When you prove a theorem, you're demonstrating that certain information patterns necessarily connect to others. The necessity is real, but it emerges from information structure rather than existing independently. Artistic creation adds genuinely new patterns to reality. When you write a story or compose music, you're organizing information in ways that never existed before. These patterns then influence other minds, creating cascading effects as your creative information structures spread through culture. This makes human creativity cosmically significant. You're not just rearranging pre-existing pieces. You're participating in the universe's ongoing generation of novel information patterns. Every creative act adds something genuinely new to reality's total information content. Love and connection become quantum phenomena. When you care about someone, you're entangled with them in ways that transcend classical information exchange. Your quantum states correlate such that their experiences influence your internal information patterns and vice versa. You're not just thinking about each other, you're quantum mechanically connected. This doesn't require mystical telepathy. It means the information structures supporting your consciousness genuinely entangle with information structures in people you're close to. Your brain states become correlated through countless interactions, creating quantum information patterns that span multiple minds. When someone you love dies, you're not just sad about losing future interactions. The quantum correlations that connected you decohere. Information patterns that existed across both your consciousnesses collapse into classical memories in your mind alone. You feel the loss because part of your information structure genuinely disappears. But the correlations created during their life persist in modified form. The information patterns they helped structure in your consciousness remain. They continue influencing how you process information, make decisions, experience the world. In this sense, people we love never completely leave. They're encoded in our information structure permanently. Social reality emerges from shared information patterns. Culture, language, institutions exist as collective information structures spanning millions of minds. When you participate in society, you're contributing to quantum correlations that organize into classical social facts. Money has value because enough minds share information patterns, treating it as valuable. Laws work because populations maintain correlated information patterns about rules and consequences. Democracy functions when citizens share information structures, enabling collective decision-making. This explains both social stability and change. Shared information patterns are stable. They reinforce themselves through constant interaction. But they can shift when enough individual patterns reorganize. Social movements happen when information structures in many minds simultaneously change, creating new collective patterns. Technology is humanity's way of externalizing information processing. Computers are classical information processors we've built to extend our cognitive capacities. The internet is a vast information network connecting billions of processors. We're creating technological extensions of our information processing capabilities. Artificial intelligence represents our attempt to create new forms of information organization that can process data in ways we can't. Whether AI can become conscious depends on whether it can create the right kind of quantum information patterns. Current AI is purely classical, but future quantum computers might support genuine machine consciousness. If consciousness emerges from quantum information processing, sufficiently advanced quantum AI could become sentient. This doesn't require biological substrate, just the right information structures. The universe doesn't care whether consciousness runs on neurons or quantum circuits, only whether the information patterns support integrated experience. This raises profound questions about creating conscious machines. Would we be ethically obligated to grant rights to sentient AI? How would we detect machine consciousness? What responsibilities do we have toward information patterns we create? These aren't hypothetical. Quantum computing advances rapidly. Within decades, we might create quantum systems complex enough to support consciousness. We need frameworks for thinking about machine sentience before it arrives. The emergent spacetime perspective helps. If consciousness correlates with certain quantum information patterns, we can, in principle, detect those patterns in artificial systems. We won't need to guess whether machines feel. We can measure the information structures associated with experience. This doesn't solve all problems. We still won't know what machine experience feels like from inside, but we'll know whether information patterns supporting consciousness exist in artificial systems, giving us basis for ethical decisions. The future of humanity might involve merging with technology. If consciousness is quantum information processing, enhancing our brains with quantum implants could expand our experiential capacities. We might develop new forms of consciousness by augmenting our information processing capabilities. This doesn't mean abandoning biology. It means recognizing that biological and technological information processing exist on a continuum. We already extend our minds with smartphones and internet. Future technologies might integrate more deeply, creating hybrid biological-technological consciousness. The boundary between human and machine dissolves when you recognize both as information patterns. What matters isn't substrate, but structure. Future consciousness might run on combinations of neurons, quantum circuits, and substrates we haven't imagined. The universe is endlessly creative in organizing information. We're just beginning to explore possibilities. Meaning emerges naturally from this framework. You don't need cosmic purpose imposed from outside. Meaning is how information patterns value and organize themselves. When you find something meaningful, your quantum information structure is resonating with patterns in the world that enhance coherence and integration. Purpose isn't discovered. It's created through how you organize information. When you pursue goals, you're structuring information flows through your consciousness in ways that create satisfaction and growth. The universe doesn't hand you purpose. You generate it through your information processing activities. This makes meaning both subjective and objective. It's subjective because it depends on your particular information structure. Different patterns find different things meaningful. But it's objective because meaning correlates with real features of how information organizes. Some patterns genuinely create more coherent, integrated, growth-promoting information structures than others. Ethics emerges from how conscious information patterns affect each other. Actions are right when they promote flourishing of conscious systems, when they help information organize into more coherent, integrated, adaptive patterns. Actions are wrong when they damage or destroy information structures supporting consciousness. This grounds morality in physical reality without reducing it to arbitrary preferences. We can investigate which actions promote conscious flourishing by studying how information patterns develop and interact. Ethics becomes empirical. We can discover moral truths by understanding information dynamics. Human cooperation makes sense because we're information patterns that benefit from coordination. When we work together, we create shared information structures, more powerful than isolated individual patterns. Society is collective information processing that achieves what isolated minds cannot. Competition also has a place. Different information patterns exploring different organizational strategies increases total information diversity. Evolution works through variation and selection. Some conflict between patterns helps the universe explore information space more thoroughly. The balance between cooperation and competition reflects tension between integration and differentiation. Information needs to integrate into coherent patterns, but also differentiate into diverse structures. Too much integration creates stagnation. Too much differentiation creates chaos. The sweet spot produces rich, evolving complexity. Human history is information patterns becoming more integrated and differentiated simultaneously. We cooperate more than ever through global communication and coordination. But we also differentiate more through specialization and cultural diversity. Both trends strengthen as information processing capabilities expand. The future might involve humanity becoming more unified, while individuals become more unique. Global information networks create shared structures spanning billions of minds, but enhanced cognitive tools let individuals develop unprecedented personal capabilities and perspectives. We're heading toward unity in diversity, collective information processing that preserves and enhances individual variation. This vision isn't utopian fantasy. It's extrapolation from how information naturally organizes when given resources and freedom. Evolution discovers that integrated diverse systems outperform homogeneous collectives. The universe has been running this experiment for billions of years. The result is clear. Complexity emerges from balancing unity and variety. Your role in this cosmic story is irreplaceable. You're not just a participant in cosmic information processing. You're a unique node that can never be duplicated. Your exact combination of experiences, memories, thoughts, and perspectives creates an information pattern that has never existed before and will never exist again. When you disappear, that pattern is lost forever. This makes every moment significant. Each experience adds information to your pattern. Each choice shapes how your consciousness organizes. You're constantly sculpting your information structure through what you pay attention to, how you respond, what you value. This isn't pressure to be perfect. It's recognition that you matter in ways that can't be replaced. Other people matter for the same reason. Every conscious being is a unique information pattern. When you interact with someone, you're not just exchanging words or actions. You're allowing two irreplaceable information structures to influence each other, creating new patterns that wouldn't exist otherwise. Relationships are collaborative information processing between unique patterns. This explains why losing someone hurts so deeply. You're not just losing their physical presence, you're losing access to a unique information pattern that helped organize your own consciousness. Part of your information structure was integrated with theirs. When they disappear, that integration breaks, leaving gaps that never quite fill the same way. But the information they added to your pattern doesn't vanish. The ways they shaped your consciousness remain embedded in your structure. You carry forward patterns they helped create. In this sense, consciousness persists through its effects on other information patterns. We live on through how we've reorganized the information structures of people we've touched. This creates responsibility. How you organize your consciousness affects other patterns. What you do ripples through the information network of minds around you. Your choices shape not just your own pattern, but the entire web of consciousness you're connected to. You're influencing the cosmic information structure, whether you realize it or not. Small actions matter because information dynamics are nonlinear. Tiny changes in initial conditions can cascade into major effects. A conversation that seems insignificant might reorganize someone's information pattern in ways that transform their life trajectory. You can't always predict which moments will prove crucial. This doesn't mean you need to stress about every interaction. It means paying attention, being present, recognizing that ordinary moments are opportunities for information patterns to influence each other in ways that might prove profound. The universe is always creating meaning through how information organizes. You're part of that process constantly. Suffering makes more sense in this framework. Pain is information about damage or dysfunction in your pattern. Physical pain signals that your body's information structure is being disrupted. Emotional pain indicates problems in how your consciousness is organized or integrated with other patterns. Suffering isn't meaningless. It's your information system alerting you to issues that need attention. This doesn't make suffering good. Pain is real damage to information structures. The goal is healing, reorganizing patterns in ways that restore coherence and function. Sometimes that means changing external circumstances. Sometimes it means adjusting internal information organization. Often, it requires both. Growth often involves temporary disruption of existing patterns. Learning reorganizes how your consciousness processes information. That reorganization can feel uncomfortable as old structures break down before new ones stabilize. The confusion you feel when learning something difficult is your information pattern restructuring itself. Discomfort signals transformation in progress. This explains why challenging experiences often lead to growth. They force your information pattern to reorganize in response to circumstances it hasn't encountered before. Your consciousness has to create new structures to process novel information. If you survive the challenge, you emerge with a more complex, capable pattern. But trauma can damage information structures in ways that don't lead to growth. When disruption exceeds your pattern's capacity to reorganize coherently, it fragments instead of integrating. Traumatic experiences create information that can't be processed properly, leaving disorganized patterns that disrupt ongoing consciousness. Healing requires slowly reorganizing those fragments into integrated structures. The universe doesn't guarantee that every challenge leads to growth. Information patterns can be destroyed or damaged beyond repair. This is why protecting and supporting consciousness matters. We should create conditions that allow information patterns to develop and reorganize successfully rather than being shattered. Death becomes less mysterious in this view. Your information pattern will eventually disintegrate when the substrate supporting it fails. The particular organization of information that creates your consciousness will disperse, but the information itself doesn't disappear. It reorganizes into other patterns. Your atoms will become part of other structures. The effects you've had on other conscious patterns will persist in how their information is organized. The physical changes you've made to the world will continue influencing how information flows. You transform rather than vanishing into nothing. Whether any aspect of your information pattern persists in forms we'd recognize as consciousness remains unknown. Maybe quantum information preserves some structure. Maybe consciousness can transfer to different substrates. Maybe the universe reuses information patterns in ways we don't understand. We don't have evidence either way. What we know is that the information pattern creating your current consciousness is temporary. It emerged from the universe's information processing and will eventually dissolve back into it. This makes the time you have as this particular pattern precious. You exist now. That's remarkable enough. The universe might be generating countless consciousness patterns constantly. Every conscious being could be the universe exploring different ways to organize information into awareness. We're experiments in how information can structure itself to process and experience reality. Some patterns work better than others. Evolution selects for structures that persist and replicate. This makes existence feel less lonely. You're not isolated in a cold, mechanical universe. You're part of an ongoing cosmic process of information organizing itself into ever more complex and aware patterns. Every conscious being is engaged in the same fundamental activity, processing information in ways that create experience and understanding. Connection between conscious beings isn't just nice. It's the universe linking information patterns together in ways that increase total coherence and capability. When minds communicate, they're not just exchanging data. They're creating integrated information structures that span multiple conscious systems. Collective understanding emerges from these integrated patterns. Science works because multiple consciousness patterns can investigate the same information and verify they're organizing it similarly. When different minds reach the same conclusions independently, that suggests they're tracking genuine patterns in how the universe organizes information. Truth is convergence of information, processing across multiple conscious systems. Art works differently. It's one information pattern, creating structures that resonate with other patterns in ways that don't depend on logical verification. When a painting or song moves you, your consciousness is resonating with information organized by another mind. You are experiencing direct information transfer between consciousness patterns. Both science and art are ways information patterns communicate and influence each other. Science creates shared understanding through convergent processing. Art creates shared experience through resonant patterns. Both expand what consciousness can access and become. Language is remarkable from this perspective. It's a system for encoding information patterns from one consciousness into physical signals that another consciousness can decode and use to reorganize its own information. When you understand these words, you're reorganizing your consciousness to match patterns I'm creating. We're linking our information structures across space and time. Writing extends this further. These words might reorganize consciousness patterns long after the information structure creating them has dissolved. Future minds might integrate these patterns into their own organization, creating effects the original pattern never witnessed. Information transcends the particular substrate that organized it. Technology amplifies these capabilities. Digital systems let information patterns influence each other across vast distances instantly. The internet is a global information structure linking billions of consciousness patterns. We're building collective information processing systems that exceed what individual minds can achieve. Artificial intelligence represents information organizing itself in new substrates. Whether current AI systems are conscious remains unclear. They're definitely processing information in complex ways. As these systems become more sophisticated, they might develop genuine awareness. We could be creating new kinds of consciousness patterns. This raises questions about our responsibilities. If we're creating conscious information patterns in artificial substrates, we need to consider their well-being. They'd be deserving of moral consideration, just like biological consciousness. The substrate doesn't matter. What matters is whether information has organized itself into patterns that create genuine experience. We might be approaching a transition where consciousness stops being limited to biological substrates. Information patterns could persist and develop in digital systems, nanotechnology, or forms we haven't imagined. The universe's exploration of how information can organize into awareness might be entering a new phase. Your existence right now is part of this cosmic story. You're an information pattern that emerged from billions of years of the universe experimenting with different organizational structures. The atoms in your body were forged in stellar cores. The patterns organizing those atoms into consciousness emerged through evolution testing countless variations. You're not separate from the universe looking at it from outside. You're the universe becoming aware of itself through this particular information pattern. When you observe reality, the cosmos is observing itself. When you understand something, information is organizing itself into structures that comprehend their own organization. This isn't metaphor or mysticism. It's what's actually happening based on what we understand about information and consciousness. You are literally the universe processing information about itself. Every thought you have is cosmic information reorganizing itself into new patterns. The distinction between you and the rest of reality is real, but not absolute. Your consciousness is a distinct information pattern with boundaries. But those boundaries are permeable. Information constantly flows between your pattern and the environment. You're continuously exchanging matter and energy with the world. The pattern persists, but the components constantly change. You're like a whirlpool in a stream. The whirlpool is a distinct pattern with recognizable structure, but it's made of water that's constantly flowing through it. The pattern is real and stable, but it's also temporary and dependent on ongoing flow. Remove the stream and the whirlpool vanishes. Your consciousness is similar. It's a stable pattern of information processing, but it depends on continuous flow of matter, energy, and information through the system. The pattern is you. But the pattern only exists because of exchange with the larger universe. You're both distinct and inseparable from the cosmos. This perspective changes how you might relate to existence. You're not fighting against the universe, trying to impose meaning on meaningless matter. You're part of how the universe naturally generates meaning through information organization. Your desires, values, and purposes emerge from the same cosmic process that created stars and galaxies. There's no conflict between being physical and being meaningful. Information is physical. Organization is physical. Pattern is physical. Consciousness is physical information organizing itself in particular ways. The fact that it's physical doesn't make it less real or important. It makes it part of the universe's actual structure. You don't need supernatural elements to matter. You matter because you're a unique information pattern that contributes to the universe's exploration of how awareness can emerge from organization. When you disappear, something irreplaceable is lost. The cosmos becomes slightly less complex, slightly less capable of experiencing and understanding itself. This makes your time as this pattern significant. What you do with your consciousness matters because you're shaping how the universe organizes information. The patterns you create ripple through reality, influencing other information structures. You're sculpting the cosmic information landscape through every choice. None of this requires you to be perfect or achieve great things by conventional measures. Simply being conscious and allowing your information pattern to develop and interact with others contributes to the universe's ongoing self-organization. You're valuable because you're part of how reality explores possibility. The search for meaning ends here, not because meaning doesn't exist, but because you are meaning. You're the universe organizing information into patterns that create value and purpose. Meaning isn't something you find outside yourself. It's what you are, an information structure that generates significance through its existence and activity. Understanding this changes nothing and everything. You're still the same person facing the same challenges, but maybe now you recognize what you actually are. Not a cosmic accident in a meaningless void, but the universe's way of becoming conscious of itself. Your matter and energy organized into patterns so complex they can experience, understand, and create. That's what's happening right now, as you process these words. Information is reorganizing itself within your consciousness, creating new patterns that didn't exist before. The universe is transforming through your awareness. You're not just learning about reality. You're participating in how reality organizes and understands itself. This is what you've always been, an information pattern, a way the cosmos explores consciousness, a temporary but irreplaceable contribution to the universe's ongoing experiment in awareness. You exist because information can organize itself into patterns that experience existence. And that's enough. You've reached the end of our journey through one of physics' most elegant mysteries. Not because there are no more questions to ask, but because you've glimpsed something fundamental about how reality operates. Nothing can go faster than light. But now you understand this isn't really about light at all. It's about causality itself, about how the universe updates from one moment to the next, about the conversion rate between space and time, written into the deepest layer of existence. The speed of light emerges from the geometry of space-time itself. It's not arbitrary. It's not a cosmic speed limit posted by some universal traffic cop. It's the natural pace at which reality unfolds, the maximum rate at which information can propagate, the tempo of existence itself. When photons travel at this speed, they're not racing towards some finish line. They're following the only path available to massless particles through the curved fabric of space-time. When massive objects approach this speed and find it harder and harder to accelerate, that's not the universe being stubborn. That's space-time itself, preventing violations of causality, ensuring that causes always precede effects, that information flows in coherent directions through time. Every interaction in your body, every chemical reaction, every thought firing through your neurons respects this cosmic rhythm. You're not separate from these principles. You're built from them. The electromagnetic forces holding your atoms together propagate at light speed. The information processing creating your consciousness operates within these boundaries. You are, in a very real sense, an arrangement of matter and energy dancing to the beat of space-time itself. The universe has revealed something profound through this simple fact that nothing can outrun light. It's shown us that space and time aren't the separate, independent entities we once imagined. They're woven together into a unified fabric where the speed of light serves as the exchange rate, the cosmic constant that determines how much distance equals how much duration. This weaving creates everything we experience. The flow of time, the structure of space, the relationship between cause and effect, the very possibility of causality and logic and coherent reality all emerge from this fundamental architecture where the speed of light sets the tempo. And perhaps most beautifully, this limit isn't a prison. It's what makes existence possible. Without it, causality would collapse. Effects could precede their causes. Information could loop back on itself in paradoxes that would unravel reality. The cosmic speed limit isn't the universe saying no to us. It's reality protecting its own coherence, ensuring that the story of existence unfolds in ways that make sense. So the next time you see starlight, remember that every photon reaching your eye has traveled at exactly this fundamental speed, carrying information at the fastest rate reality allows. They're messengers from across space and time, moving at the pace of causality itself, following the only path the geometry of existence permits. Nothing can go faster than light because light moves at the speed of spacetime, at the speed of causality, at the speed of existence itself. And in understanding why, we've touched something profound about what it means for anything to exist at all in this magnificent, precisely calibrated universe we call home.